Maybe we can create some type of system in KDB that will catalog and gather metrics about objects within that database or list of databases. So if we look here, this is the page that describes what KDB databases are and the different type of objects that can exist within them. And so there's different examples. This is the simplest type of table, and then this can also be other entities in Q. It can be tables or dictionaries or key tables or lists of tables or compound lists, anything really. We can set, when we use the set function, it sets that down as a object, as a single binary file. So that's one possibility of entities, objects which can exist within a KDB database. Another object is a splayed table. So in this case, it's not just a file, it's a directory. And the name of the directory is actually the name of the table. And inside the directory, there will be multiple files. And each file represents the data for a column. And the name of the file is the name of the column. So a partition table is pretty much the same as a splayed table. It's just another level of hierarchy within a directory. So instead of just the database root directory and then the table, a directory which contains the table name, we have the database and then a partition and then the table name. So we could have the database multiple partitions, for example date, so we could have all the dates of the year, 365, and inside each one of those we would have a splayed table which would contain the data for that table for that date. And so that's another form of a object, a KDB database object. We have single binary files, we have splayed tables, we have partition tables, and then the last is segmented tables. So here's the example of the splayed table we talked about. So quotes is a splayed table, and we know that because it is a directory and it contains files, and each file is the columns. And here's another splayed table that contains these columns. Here's an example of a partition database, partition tables within a database, quotes and trades. And you see these are splayed tables here. So this is a splayed table that exists inside another directory, which is called a partition. So when a splayed table is in a partition, it's a partitioned table, because this is a slice of the data for this date, and this would be another slice of the same table. It's still quotes, it's just represented, it's just in a different directory, and that directory is called a partition. So this is a partition table. Two examples, quotes and trades are partition tables, and here quotes and trades are splayed tables. And here quotes and trades are flat tables, so binary tables. And segmented, we'll not worry about that for now. So we can see here when we save a splayed table, and this applies for partition tables also, and we can see that a hidden.d file is created within the table directory, the splayed table directory. And this file actually contains a list of symbols, and that list of symbols represents the columns and the column order of the associated table. So this is an important file. This defines the column names and the column order. It tells KDB when you load the database, when you load this table, it will tell KDB which actual files, column files to look for and to map into memory. And if they were not found in here, they will not be loaded. So the reason I'm showing this is because we want to write some type of system that can incorporate all of these considerations and get useful information from objects such as binary tables, splayed tables, partition tables. We want some type of logic that can handle, firstly categorize such objects within a database, and then gather metrics about such objects. So we would want to, in our logic, we would want to get the list of files within the splayed table directory. We would also want to probably read in the .d file, and you can already imagine we could start doing comparisons there. So is there a discrepancy between what's represented in the .d file and what's actually in the directory? If so, that would be something we would want to know about. If you imagine this in some type of production system, that's a critical issue. And you can think of other things we could do. We could go inside each of these. We could separately, each column, we could take a count, say, and we could compare those and see is there any discrepancies in the counts of the columns. That would be a issue. Our database would be corrupted if that was the case. If in a single table there was a different count of each column, that should never be the case. We could also get the data separately and check the actual data, like what type is the data? Is there multiple types in a single column? Is there null values within that column? Different things like that. Does the column conform to the attributes that have been placed on it? So these are things that our program, our non-existing program, could check and report on. We could also check is meta, the function meta, if we run that on the table, does it report the same information that we get from .d and the files, etc. And if this is a partition table, are these answers the same across all partitions? Because that's a consideration we need to add for partition tables. And we can see here when we're dealing with splayed tables, sometimes multiple files are stored for the same column and they have the same name, except one has a hash at the end of the file name. And we know this sim file is created within the database root directory, and it's for enumeration, symbol enumerations for all tables. So on my computer I already have old projects. I only have a few. This is a more recent computer, so I've only got a few more recent projects here, but I've got databases, existing databases. So maybe I could even use those as inputs to this program. Hopefully I've got partition databases and splayed tables and flat objects, binary objects within different databases. So I'll try that. So let's create. So like maybe your first thought would be to just load the database as you would normally do in Q with a load statement, but if the database is corrupted, maybe it will not load. If the database is corrupted, it won't load, so that would not work. And even though it may throw an error that could help us in figuring out why the database didn't load, it doesn't account for multiple issues within a database. So it would only stop at the first issue. So we want to just maybe use Unix commands or system commands to get a list of files rather than say loading the database and doing tables, trying to run tables, loading DB, and then trying to run such functions. So this is the empty script, and we'll start. So we have a list of databases. These are databases I already found that already exist on my computer. So I can show you just an example. So this directory, this is the database root directory, and it contains multiple objects. Some of them are scripts, some of them are binary tables, or dictionaries, or lists. Some of them are directories, and those directories which are dates contain partition tables. Those which are just table names are splayed tables, so these are splayed tables. So this database has multiple different types of objects that we could expect to find. And this is just one example of a database. We have other ones here too. So we want it to run for a large collection of databases. Another piece of code I'm just going to add. And you can see this function has it takes 3 parameters and 2 are pre-supplied here. So .z.u is the current user, which is Michael. .z.h is the current host, which is this. And then it concatenates that as x and y with the current time. And then the last variable, which it awaits here, is referenced as z inside the function, and that's the actual message that's passed in. So this is just the utility function we're going to store and include in our script. So we have another function here that I'm going to copy also. And it's called .util.fileinfo. So let's run that also. Okay, so this function uses the Unix file command, so we can do that here. So if we do file dbi, it returns ASCII text. So it's telling us the contents of this file that we supplied is ASCII text. If we do it on something else, for example, this, it tells us that this is a directory. If we do it on, say, this file, it tells us that it's a data file. And in Q, so we can give the key of a path is the files contained within the path. So that'll be all files within the path, all objects within the path. So that's files or directories. So we created a list of paths, and each path was the file contained in that particular, the object contained within that particular database root directory, which could be a directory, it could be a data file, it could be an ASCII text file, it could be other types of objects. So then we ran the .util.fileinfo on each one of those, and that returns this dictionary, which contains the object and the type of object. So we'll store that in a variable. So now we have the types of each object within the database root directory. We want to probably start categorizing them, or maybe just using this information as additional information to aid in our categorizing of the objects. So let's say it, so splayed part. So how do we find which objects are splayed and partitioned and what those objects are? I'm thinking we can use this .d file. So it is contained inside every splayed table, and sometimes that splayed table is itself within a directory. So we'll be able to identify which tables are splayed and which are partitioned. Okay. So if we were to do a find command, and where the directory is just the db path, so this is just a system command, a Linux command, and this will search for the presence of a file called .d. within this directory and all subdirectories. Okay. So we can see here pretty quickly the only entities or objects which will contain a .d file are splayed tables. And those splayed tables which are in two levels of hierarchy from the database root directory are partition tables. Those which are just one are splayed tables. So we could probably use this information to programmatically choose which or label which tables or objects are splayed or partitioned. So these, because the count is only one, that means it's in the first level of the database root directory. That means and it contained a .d file. That means it's a splayed table. Okay. So now we should probably get all this information and pass it back into the calling function. So this has just went into the database root directory and it has categorized flat tables, splayed tables, and partition tables, and it has given us the list of specific partitions also. So we got the names of the splayed, flat, partitioned, and we got the names of the partitions also. So we can see it ran for each of the items within this DB list, and it has categorized them, created this dictionary, and returned it. And we've stored that in a variable called dbinfo. So if we look at this, so this is for the first database. And if we look here, it shows all of the objects within the database root directory. It shows the types, so we can index into this object. We can see the object types. And then we can see that it has catalogued the splayed tables, the partition tables, and the flat objects. The binary flat serialized objects. So now we would want to pass each of these objects into a new function that will then analyze each of these objects that we've labeled and gather specific metrics. So if we have a splayed table, we want to look inside that directory, find the columns, and do analysis on the columns. Okay. So this is a list of paths that point to each splayed table. So I didn't record this adding this code, but we can go through the whole thing now. So let's go through the actual script. So when we load the script, like so, first it runs from top to bottom, and it kind of parses each unit into a unit. So I would say this is one unit, 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 this is one unit. So here in all these cases, apart from here, so this is actually just setting the console size, but all of these are just declarations of functions or variables. Only until here, this special line here, do we actually execute any of the code that was declared above. So all of this is just defining things. Nothing is actually done. There's no actual logic ran when we load this script. Only until we get to this point, line 81 at the very end of the script, will anything happen really. That is our entry point into our logic. So if we ever want to understand how a script works, we need to find where the entry point is. Once we get that, we look at the function that it calls, and then we can start figuring out how things work. So when we go in, so we know now that when we load this script up until line 80, we're just declaring things. On line 81, we actually execute. When line 81 runs, it goes into the run function. Line 76 is ran, which just prints a message to the console, cataloging DBs. The next line, 77, it takes each DBs, which was defined when we first loaded the script, and it passes each one of those into a function called catalogue DB. So each one of those paths are sequentially passed into this catalogue DB function. We went through what happens in here. So we get the database path, and we do the key of the path, which returns all files within the path. So we know in our case that can be tables, binary tables, splayed tables, partition tables, dictionaries, different types of objects can be stored within the database root directory. So we just get all those out and we store it into the variable called all files. We print out a console message telling us the number of objects we're going to catalog. We use this utility function .util.fileinfo to run the Unix file command on each one of those found objects. That will tell us what type of object it is, whether it's a data file, whether it's a directory, whether it's an ASCII text file, or something else. And we already with that type of information, we can already distinguish between certain types of KDB specific objects. If they're found within a database root directory and they are a directory themselves, that means something within the context of Q. So we're collecting this information and other such information in the subsequent code to kind of figure out what KDB specific objects these are. So on line 63 we use the find Unix command, and we search within the database root directory for any files that are called .d, and we can see from here .d is a hidden file that is stored within each splayed table directory. And from that we get either splayed tables or partition tables. In the case of splayed tables, there's only one level of hierarchy between the database root. In the case of partition tables, there's two. So we use that feature to pick out which tables are splayed and which ones are partitioned. So you can see here, if there's one, it's splayed. If there's two, it's partitioned. And then lastly, we do this operation, which finds all the objects in the database root directory which are just flat binary serialized objects. And we call those flat. We log out our findings and we return all of that information to the calling function. So if we recall, each database was passed into this function. It returns, in each case sequentially, it returns a dictionary object, and then each one of those dictionaries is passed into this function, catalogue db objects. So this is the database object, the object for a particular database that contains the useful information about the tables, splayed tables, if there's partition tables, and what those partitions are. And so that's passed in sequentially now into catalogue db objects. So for each database, it will be passed into here, and we will then catalog each type of object we're interested in. So splayed, partitioned, or binary flat objects. So first we're doing the splayed objects, and we pass the path to each splayed table into the function catalogue splayed. When we go into catalogue splayed, this takes obviously the path to the splayed object, and we do a safe evaluation of this function. The parameter is the path to the splayed table, and if it fails, we will run this function. So this syntax means it's kind of try catch. So try this function with this parameter. If it works, it returns the result of this function. If it fails, it returns the result of this function, where x is the error that was encountered. So we run this, these two lines on the table, the splayed table path. So this is a HSIM, this is not data, this is not we haven't selected from the table, we haven't loaded the database, we're just passing paths, and we're running operations that can run on paths. So we run calls, and then we run meta, and we store those in their associated local variables. We then create a path to the .d file, the special .d file, and we actually pull it from disk. We read it from disk with this get function, and we also do that safely in a try catch. And if it fails, we return an object that's the same. It's a list. The first item is always false, and the second is the actual error string. So T files then is, we do key of tpath. So this is a splayed table, it's a directory. When you do key of directory, it returns all the files within that directory, all objects within that directory. So from that list of objects, we exclude those which end in a hash. So that excludes the extra column files for specific types of columns. So we exclude those, and that will leave the original column file in the list. And so that gives us a list of all files within the splayed table directory that don't contain this and aren't the .d file. And so from this information, we can start declaring other things or defining other use. This is the actual useful information down here. So for example, if you imagine in a D file, you read a .d file and it will give you a list, a symbol list of columns. And the order of that list is the order of columns that the table will have. So you obviously want the same order in each .d file if you're dealing with partition tables. And you obviously don't want a case where you probably don't, or we want to report on cases where there's duplicate items within a .d file. Maybe if there are items in the .d file but they aren't referenced in, the object doesn't actually exist in the splayed table directory. Or if there's objects within the splayed table directory which aren't referenced in the .d file. So these are all probably cases we would want to know about. We want that data and we want to parse or store that data or do operations on that data, report on it. I'm not sure, but we want it. So I think there's a few cases that I didn't actually incorporate here, and we'll do that. So first we'll actually run the code and we'll stop inside here and take a look. So here we're analyzing the table called test table, and it's been identified in the upstream code as being a splayed table. So it has a .d file inside of it. So if we do key, it will show all files within that directory. And here you can see those special type of files with the hash at the end, and you can see there's other files. So when we exclude them by this, with this piece of code, it will leave us with a set of files that exist within the splayed table directory, and then we can use that to check against the .d file or against what meta returned or what calls returned. Okay. So it has to be 11H. That means it's a symbol list. If it's not a symbol list, it's a bad D file. And we want to include these into the returned object. splayed, we go inside catalogue splayed, and then we start probing the path. So we do calls path, and we do it in a safe manner where it's error trapped. We do meta on the path, and we get the D file, and we read the D file in, and that should give us the list of columns. We check if that list is type 11H, which is a list of symbols. It must be a list of symbols. Then we also just look inside the directory of tpath of the splayed table. We look inside the directory and just get the list of files. So that's the list of files which don't have this hash at the end and aren't the .d file. We've defined the unused columns, so these would be any columns that are in the .d file but aren't in the actual splayed table directory list of files. We have this variable called missing calls, which is the files that are in the directory but they aren't referenced in the list of columns in the D file. We have duplicate columns. This variable is called dup calls, and that's a list of columns where it's referenced more than once in the .d file. And then this variable good calls is which columns in the .d file are also in the list of files within the database table directory, the splayed table directory. So then for this list of columns, these good columns, that this may be overkill, but let's do it anyway, there's no harm in it. So let's define the good columns as any columns that so the good columns are ones that they must exist in the directory. I'm wondering, should we still process those even if they aren't in the actual D file? Or we could just ignore those for now. So here we return we define a local variable called good calls. So these are the good columns, and those are the columns which are referenced in the .d file, and there's also an associated file in the splayed table directory. So there must be a file that exists that contains the column data that's referenced in the .d file. Then we create a path for each one of those, which is the path to the table, and then inside that is the column name, is the file which is the column name, and then we pass that each one of those paths into this function. So this function, I think later we'll do it in a error trap fashion, I'm not sure, but it actually reads the column data in and it pushes that data into the function called catalogue column. So let's look inside this function. So we can see here the data, call data, has been passed in here. So this is for the first column path. First we do a count on the column data, so this is a count on the file that we just read in. In this case there's 476,823 records. And of course this is a single table, so when we count the next column it should be exactly 476,823 because it's the same table. And if it's not, we want to be able to report it, and we can with this code. That's why we're doing each column separately. So this is the value count. Here are the value types. Here are the value types. So here we do the default type. We try and figure out what's the default type. So we group the types. So this v types is the type of every single record, every single column value. If there were multiple types, there would be multiple keys, and then the indexes of where the type is different. And if there were multiple types, there would be multiple records here, and the largest would be the most common type, and that's the type we define as the default type. So here we just check, are there any instances where the type of the value is different from the default type? Show us those. In this case there's none, because this is a properly structured column. So this will be ran for every column. So here, this is ran for every column. And then it's passed back to the function that called it. And it's stored in this local variable called splayed info. And then we need to do the same or a similar thing to each parted table. So first let's check out this result. So if we index into this dictionary now, and we want to look at one of our splayed tables, it will return all the associated data that we gathered for those for that splayed table. And we did that inside the catalog splayed table, which took the splayed table, got information about the columns, the good columns, duplicated columns, missing columns, and then it also, for each of the columns, it gathered information about the column, like the count, the types, if there's nulls, and it added that to the returning object, and we see it here. And so we have this information for each of the tables, each of the splayed tables. So we can see here this actually failed because there's no sim file defined. Okay, so we could not run the meta function on this table path. Yeah, we could not run the meta function on the table path because this file does not exist. This variable does not exist globally in the current cube process. So when we're cataloging these DB objects, we probably want to load a sim file if it exists, firstly. So in DB info we have the database path, and we can just add on sim to that. Okay, so it's printing out this also. And we want to get it. Now, since we're looking at corrupted databases, probably, or maybe, we want to make sure that doesn't fail if a sim file doesn't exist. And in some normal databases, there is no sim file. So it should not fail if there isn't a sim file. If there is, though, it should read it and store it as a global variable called sim. So we'll do that inside a protected evaluation statement. So the first item, first parameter is the function to try. The second is the parameter to pass into the function, which is this path. And the third is what to do if the function fails. So what we'll do is just return 0b and the error. And the function is going to get x, where x is the path to the sim file. And then it's going to set that to a variable called sim, a global variable called sim. And now sim exists. Let's rerun this and see, do we still have that sim error? So here we can see we have the meta information now. It did not fail due to the sim file. Okay, so this splayed table actually does contain some errors. So there's a column, an unused column, which is called clinvar, and there's a missing column, which is zyg. There's no duplicate columns, and the D file is okay. It works. Table meta failed due to some error. We can look at that now. So there is no such file as clinvar. And we know why. We know because it's an unused column. And we can see we defined unused columns here. So those are columns that are in the D file, but there is no actual data file in the splayed table directory. So that cannot exist. We must remove the reference from the .d file, or we must add the data file to the splayed table directory for this error to resolve. This should never happen in a database. In a KDB database. Now we'll do the same thing with partition tables and figure out how to do that. We already have a skeleton function, an empty function. I will just use it. So this is the name of a... So we shouldn't actually do this because this is a partition table. In this case, we'll pass in the database path. So this function should take in 2 parameters. Where the second parameter is just the name of the table. Let's just pass in db info. So these are actually paths to splayed tables. So we could maybe just pass those into our existing function, which expects a splayed table, and it will catalog all the information about it and its columns automatically. Let's try that. Okay, so it seems to have ran for each, so it's returning a result for each table, each partition pretty much. So we should probably just add on another column to this that references the partition that this result comes from. Okay, so these are the results for the two parted tables, partition tables. And we should update the item within the DB info object with the found information, with the information, the catalogued information we added to each partition. So we did a similar thing last time, like here. So we'll do that. So here we can look at dbInfo, which is the object that contains all the information about the database and objects contained within, down to the column level. And down to the column value level, we actually check each value in each column for the discrepancies, like type discrepancies or nulls. And we also store information like the count of the column that we can use later. Now we have the information we need. So this process gathers information, it catalogs objects within the KDB database. And now we'll just store that to our own database. So let's define that. Okay, it took 11 seconds and it stored the data here. So we should be able to quit queue and open a new process, a clear process, and load that table. We can investigate it. Let's add some error trapping or something finally. Let's run the whole script from start to finish. We productionized it a little bit by adding the configurable options, but it's not perfect. But this is good now. We get all the information, we save it to our own little database directory, and then next time we can pick that up and analyze the differences and report on them, maybe create, so we've just created the base data that we can build some type of interesting system on top of. So let's run it again from start to finish. Yeah, that's about it. we'll continue on where we left off here next time. Good luck.